Hey, what's going on, guys? Easy here. So I'm back here to implement LDY instruction with all the possible available addressing modes. So let's open the terminal in the current working directory, and by running our run.shell loop, we'll have a look at how the output looks like so far. Alright, so we ended up with a absolute address and the Y offset, so 92, okay, 01, 04 plus 1 in Y. Yeah, so just trying to recall this from the previous part. Okay, so we are continuing our work. So now I will, well, I'm not sure, should I actually, well, what I need to do for sure is I just want to grab this unit tests we've written for LDX, and I want to copy them to the unit test.asm backup file. The code is not doing anything there. I just dump it there because otherwise the amount of random access memory being used for this is growing extremely fast, and I don't really want that to happen, basically. So yeah, okay. So here we don't need this. We don't need this, and paste. And just grab some, or no, I can grab from, yeah, just here, and here we have LDX. Okay, so let's have a look at the list of the opcodes. So LDX is now completed. Now the next thing to consider is LDY. So load data to the Y register. Okay, so immediate seems to be the same, 0 page seems to be the same, then the 0 page and X offset is instead of Y offset for LDY, and for absolute X instead of Y. So it's very similar. So yeah, we're going to be reusing the code and the tests we've written for LDX. So yeah, just going to be reusing this entirely. So let's kickstart by this very first one. I just want to copy and tests, unit tests here. Okay. Oh, thank you, sir. Okay, so test 001, starting from scratch again, so I don't want this anymore. Yeah, so now it would be just running the test for LDX. Okay, test for LDX. Sorry guys, just my wife has just started talking on the phone. I was a little bit distracted by that. I thought that she was talking to me, but fortunately not. Okay, oh my god, it's really hard to concentrate sometimes. It's really hard to concentrate. So yeah, I just want to have a look at the output. So currently, so yeah, so first I need to, okay, maybe let's just go the way we did in the previous part. So would it be just bringing the pieces of code and just to not to miss anything, the commentaries, etc. So yeah, we'll start by altering the source bytes of 6502 assembly, and then we'll go further on. So where did we so we've stopped here, right? So the next one is this, and here we have A0. Okay, A0, save A0, was it? Yes, A0. So I'm initializing the local variable holding our test program. So I'm just wondering, yeah, this is just the code to set up the zero flags. Well, this might be zero negative flag. Yeah, this is just okay. And here I want to say a 0, and it represents LDY. So load the value of hexadecimal 24 to the Y register, right? Okay, so now I want to, so yes, debug in strings, and now I want to see this code. So A024, which is correct. Okay, then, no, don't execute for now. So the starting values for, so the registers, so we've just, I just set the negative and 0 flags just to make sure that it would reset them back when occurs non-negative and non-zero value. By saying negative value, I mean not obviously signed, might be unsigned, but in this case, if it contains the most significant bit being set to 1, it would still be treated as the value affecting the negative flag. So it should be 2, 0 after, because 2 is just the reserve flag, which is always set to true. Okay, right, so now it's time to, so before we call and execute, now it's time to implement this. And by the way, so probably just comment this out. Yeah, just, it's always a good idea to add some extra separators. So here we had LDX, and now we're coming to LDY. So I want to compare whatever we have in the AL register. So we just load the next instruction from the user source code that has been loaded into the emulated memory of 6502 emulated or simulated memory. So the source code is there. We've seen that, we saw this. So you see, like at this address where the source code lives. So just fetched the opcode, and now depending on what the opcode is, we need to take a decision on what instruction we have encountered, and we then need to execute that. So here it is LDY immediate addressing mode. So is it? If so, I want to say jump equals to LDY immediate, and if so, then execute it. Not the most exciting commentaries ever, but I'm doing this for my own self, just not to get lost after. Okay, so LDY immediate addressing mode. Yeah, and now we can just reuse our LDX immediate, and all we need to do is to change the register to load data to. So let's try to find one. So LDX immediate addressing mode. So if I just grab this and paste, and here I want the LDY, and here LDY. Okay, and we want to load the data not to the X but to the Y register. And if I did everything properly, this should be fairly enough to execute the instruction properly. So let's call the execute, and let's print the debug info, what it's gonna be after. So let's have a look. So the value of 24 has been loaded to register Y. This is the immediate data. Program counter has increased by 2, which is correct because we only have 2 bytes. The flags has been restored, so the bit that was making this value A has now been reset. So it's 0, it's 0, 0, 1, 0. Only the reserved flag has been set, which it always said it. That's just the default value. Okay. What else? Yeah, so negative flag was released, and the 0 flag was released as well. So we don't have those because this value doesn't have those. Okay, yeah. just a quick look at just want to check my code, check my code that clears. Okay, so I'm just clearing the 0 flag and the negative flag using using the mask right here and here. Yeah, this should be fairly enough. All right, okay, so now let's adjust the test cases. So as far as we've check everything out manually. So register failed, but it should be 24 in the register Y. So the register Y should contain 24. And this is test Y register, right? Okay, so it passes. Then all the flags should be the same, and the program counter should be also the same. So yeah, flags passed, program counters just from the previous test, so it's the same, passed, all done. Okay, so hopefully this is about to be working. Okay, now we jump into the task 2. So did I? Yeah, adjusted the code. Yeah, it seems like I did everything there. So test number 2, and this one is load data from. Yeah, and by the way, here in the commentaries, I just forgot to change one. All right, save, and just want to make sure LDY 24. Right, so LDY from the 0 page address 04. Okay, so far so good. Yeah, let's start by commenting everything out. I could have not been doing that, but I just don't really want to miss. I'm still missing this tiny minor errors in the commentaries, so it's really better to go kind of like step by step. So here, initializing the test program, so the opcode should be different. It's okay to have the same value to fetch data from, but I want to change the opcode, and I need this one, A4, so load 0 data from 0 page to the Y register. A4. Okay, so A4, right. Let's have a look what we got there. So, okay, just got the code. Okay, now here we also need to set up the value at this. So memory address +4, this is the absolute address of 0 pages from the x86 bootable environment perspective, from the real mode perspective. And also we want to print this. So we have 0, 1, 2, 3, 4, and here we have the value of E5. So now the value of E5 should be loaded to the register Y. Okay, seems like it's okay. So the state of the register is from the previous part. So we have 24 in the Y from the previous instruction. So we didn't reset the CPU, we didn't reset the memory as well, but it's okay. So now we're going to fetch this one. Okay, so before executing, let's implement this instruction. So here I want to say compare AL with instruction LDY 0 page. So this is LDY 0 page addressing opcode. It's not the mode, it's mode, but we're referencing not the mode but opcode, or opcode for a mode, but I've been using the opcode here because AL actually holds the opcode, the operation code. So 0 page opcode and jump equals LDY 0 page Y, but we need the 0 page X. So LDY 0 page X, right? And I believe this might be grabbed from the LDA, but no, we just better grab this from LDX. Okay, so LDY 0 page X. If so, then execute it. LDY 0 page X. So now I want to find LDX 0 page Y, this one. I grab it and bring it in, and now this is going to be LDY 0 page plus the X offset. So this is going to be LDY 0 page X offset. And here we want to add the value at the X register, and we want move byte to the Y register. And the rest should be working. But I'm a bit concerned about the fact that we actually initialize. So we need to bring 1 to the register. We need to bring 1 to the register X to make it work. Oh, no, hold on a sec. It's not. It's gonna be. Oh, or no, or it is. Okay, hold on, guys. I'm already lost. Okay, so why the heck do I try to implement the 0 page plus offset when it's just a matter of a bare 0 page? That's the good question. Yeah, so that's the good question. So you're welcome, man. Okay. Yeah, that's a bit of an issue. So 0 page. Well, I'm not going to be deleting this. I just command this out for a while. Because nope. So actually, I've cloned the one with the offset, but all I need is just to clone the one without the offset, because this is just referencing 0 page without any offset. So LDY and here LDY 0 page. All right, just loading the data to the Y register, and everything else should remain the same. And in the execute, this is 0 page address number. So why the heck do I make it like this? It should be like so, literally. Okay, and yeah, now we'll check this out. Call execute and see what we got in return. And we got an error. All right, LDX 0 page undefined 370. Oh my god, I've commanded the wrong. Oh my god, I've commented the wrong one. Yeah, so probably I needed to comment out this one. Yeah. Okay, this is much better. Okay, so Y register has the value of E5, which is correct, so it has been fetched from the 0 page 0, 1, 2, 3, 4, 0 page 4 as mentioned here. Alright, so opcode A4. Let's make sure everything is working properly. LDY is 0 page, LDY 0 page. So yeah, as far as it gets here, it should be the correct opcode. All right. Yeah. Okay. So now let's check out all the stuff. So it did set the negative flag because E has the most significant bit being equal to 1, which is correct, and increased the program counter by 2. Yeah, it seems to be. So the main thing is just gets the value to the Y register, and it does. All right, so now the Y register should be like this. A0. Why this just lowercase? Doesn't matter. Just okay. So this should actually now pass everything. Yeah, so we have the value. It matches because it's just from the previous test, and I just changed to compare with the Y register, with a byte at the Y register, not with a byte at the X register. So program flag, processor flags. Okay, yeah, seems like it is just fine. Well, great. And now finally we're going to this one. So yeah, test 3, and here we go. Copy. Yeah. So jump to test 3. This is okay. Yeah. Okay, let's grab the opcode. So LDY, 0 page and offset X, and B4. Okay. Who likes developing bishop on B4 in chess? Okay, so this is gonna be B4. Okay, and this is gonna be LDY 04 plus the X offset. In this case, this is important. Okay, so here to the X register, not to the Y, to the X register, we need to it needs the value of 1, and that's going to be serving as an offset. Okay, so test program, loading, initializing, and printing the test program. So it should have the bytes B404, which is correct. Okay, then at the address memory plus 5, so it's 0 page 4 plus 1, 0 page 5. There we put this value of F8 hexadecimal, just an arbitrary value, nothing special really. And then we want to print what we have in the memory. So in the memory we have this f8, and this is the exact value that we're going to be fetching using the LDY 0 page plus x addressing mode. Okay, so let's print the debugging info, and then we'll go for executing things. Okay, so 1 in the X register, which is okay, so it should take the 0 page of 4 from here and then add the value from the X register and get here actually. So yeah, let's go to the implementation. So compare AL with this. So LDY 0 page plus X offset opcode jump equals to LDY 0 page X. And we already have that accidentally, but anyway, if so, then execute it. So let's scroll down a little bit. Yeah, here it is. So should be working already. So we're adding the value from the X register and loading the value to the Y register. Yeah, let's see if this is going to be working actually. So execute and print the debug info again. Okay, we got the F8 in the Y register, comes from here, right? So 0 page 4, 0, 1, 2, 3, 4 plus 1 in X is going to be 5, fetching the value from there, which is F8, put into the Y register. The negative flag is still being affected, hence not changed, and it takes 2 bytes to increase the program counter. Well, everything seems to be working properly, so let's adjust the test cases. So we want to test the Y register if it is equal to F8. Test Y register. Test Y register. Okay. Flags are the same. Program counter is the same, so it should be passing now. Okay, all done. Yeah, this is nice. So F8, so the most essential thing, the value that we've fetched from the 0 page plus the X offset, which is okay, which is correct. Okay, perfect. So the next thing to consider, we want the absolute value. Yeah, here we have the LDX and the Y offset. This is correct. And now this one. Yeah, let's go with this one. Copy. Say jump to 4. Paste. Right. This is boring, I know. This could be automated and optimized, but I don't really want to write tests that would be testing the tests, so I would just rather spend some time on commenting and uncommenting code out. Yeah, let's bring the separator just to have it visually a bit better representation. All right, so let's go and grab the opcode. So LDY absolute address AC, save and copy, and we're looking for a test 004. AC. So here we do LDY, and we load the value of the value from 0104. Okay. Yeah, let's see. Oh, third ABS dressing mode. Yeah, all this should be fine. Yeah, let's bring the program in. So AC 0401. So the because of the little endian order, we have not 0104 but 0401. The bytes are swapped. So this is predictable, all right? Then we need to set a value there, and we set in the value of 73, and this address 0104 in the emulated memory plus the offset of where the emulated memory is to get the absolute one, right? So let's print what we have. So yeah, here is the absolute memory address. So you can ignore this E, so you might be thinking of this as 0100s, 0100s, 101 and 2 and 3 100s and 4. So 0104. The value here we have is 73, but it's encoded in the little endian. So just to bear that in mind. So now we should have the value of 73 in the Y register. Okay, so let's print the state of the registers, the CPU state literally from the previous iteration. Yeah, and now it just should put the value here. And by the way, the flag should get resetted because no longer the negative flag is no longer going to be on the cards there. All right, so let's implement this one. So here I want to say compare real with instruction LDY absolute addressing. So is this the LDY absolute addressing opcode? If so, jump equals to LDY ABS. All right. If so, then execute it. Okay. Yeah. Okay. Yeah, now let's go and implement this. So I'm looking for LDX absolute. I'm just bringing them kind of like all together. LDA 0 page X, LDY 0 page Y, LDY 0 page X, LDA ABS, LDX ABS, and here copy, we will have LDY absolute address and mode, LDY ABS. We want to load to the register Y and increase the program counter by 3 because we have 3 bytes to fetch now, and this should be working in theory. All the rest should be working. Yeah, let's have a look. So execute and print the state again. So 73 we got, yeah, 73 in the Y because that gets from 0104, 00, 01, 02, 03, 04. Okay, so 73 goes here, stripping the negative flag. All right, and the program counter gets increased by 3. So 06, now 09. Yeah, seems to be just fine. Now let's bring the test cases in. So we're comparing with the register Y and test the register Y, and the rest should be working. Let's have a look. Yeah, so it seems like it is 73. sorry guys for I'm pronouncing this and telling this kind of enormous number of times. To be honest, I'm not doing this for you, I'm doing this for my own self, and that's how I do if I'm not recording the video. So just a live coding, that's how I develop basically. Maybe not the best ever way of doing things, but that's how I do things, and it works for me, and that's good enough already. Okay, so yeah, this is pretty much all about it, right? All done. I'm missing the error messages from time to time, but it doesn't seem like this case. So yeah, 73 flags, program counter. Well, it seems to be just fine. It seems to be just okay. Great, and the very last one in this case, yeah, so this is gonna be the absolute and the offset and the x offset, right? There should be the x offset. So that's number 5, and bring this in, and here we go. From this video you will learn how to comment out assembly code. Yeah. Okay, so let's grab the opcode. Yeah, and we are done with the load operations. BC. This is really awesome. So I'm looking for a test. BC. Sorry. Hold on a sec. Not so fast. I want to grab this one. Copy. Test 005. BC. So we have the BC. This is going to be LDY and the X offset. So we use the same address, but now we're going to be using the offset as well. I'm just wondering, yeah, will we use the value of X? It's still equal to 1. So yeah, this should be still on the cards. Let's have a look. So we still have, okay, BC 0401, little endian, okay. Yeah, so now we set the value at not 0104 but 0105, the value of 92 hexadecimal, and let's see the memory. Okay, so this 92 is now about to be fetched from this absolute address, right? And the processor state, so we have, yeah, we have 01 here still, which is good. So we're going to be using this X as an offset for absolute addressing plus X offset for LDY. Yeah, now let's go and implement this here. So compare AL with this one, and say LDY absolute addressing plus X offset opcode, and if so, I want to say jump equals to LDY ABS X, just like similar to this one. All right, if so, then execute it. And now we're looking for LDX ABSY, LDX ABSY, LDX ABSY. Yeah, so we'll take this one as a template, copy, paste. So this is going to be LDY, absolute addressing, plus X offset. Here we have LDY plus X. Okay. We are adding the value from the X register, and we're loading the value to the Y register and getting the absolute value. Yeah, now this should be working, hopefully. Let's have a look. So execute and see the state. Okay, so we got 92. Awesome. So 9 sets the negative flag because it has the most significant bit in it being equal to 1. So A0, this is correct. So 0, 0, 1, 2, 3, 4 plus 1 in X, ABS plus Y. Hold on a sec. Okay, guys, there are gonna be one thing a couple of minor errors to handle. The labels are a bit wrong, so I need to change the labels. Actually, it seems to be working properly. The value is okay, and 9 A, B, C plus 3. This is okay. Flags are okay. So yeah, everything is okay. I just need to handle the. So this is Y, test Y register. I just need to. This is okay. All done. Yeah. There are a couple of issues here. So the first one is the 0 page. Yeah, the 0 page and. I'm just dropping it so not prints the entire thing. So 0 page addressing is correct, and here we got a bit of an issue. So for instance, so it's not 0 page and Y offset. Actually, this is technically this is 0 page and X offset. So test 0 page X. I should have that already. I should already have that. Yeah, now 0 page and X. Yeah, now this is okay because we actually have the X as an offset. So restoring the value back, and now in the very last test, the same scenario. So test ABS X. All right, so ABS and the X offset addressing. Yeah, so 92 goes to the Y register, so X is still here. Yeah, now this seems to be just okay. So yeah, I just needed to make sure that the labels are matching, because if an error occurs there one day, it would be misleading a little bit if we have just not matching a non-matching kind of like labels, right? Okay guys, so congratulations, we currently have all the load commands to all the registers for all the addressing modes being implemented, and this is really cool. And now we can easily do the same but for set operations, and it even takes less work to do. So this one is significant, including the indirect addressing, which is quite pretty, not that trivial to do, but anyway. But for X, set X and set Y, really miserable amount of instructions. And from there on, the only I'm wondering, so yeah, for AND or E or, I'm not sure what the E or stands for. Yeah, so there are quite a few operations that works only on the A register and involves all the addressing modes. Yeah, and yeah, that takes work to do. But again, like it should be trivial as well. So just changing the operation to and or whatever, right? Yeah. So even though there are tons of operations still kind of left, and when I've been grabbing this instruction from Dave's tutorial, so there is a guy on YouTube has been doing emulating 6502 processor in C. I've grabbed the opcodes from there. I really hope that these are all the opcodes that we need. However, I'm not really that sure, so still I would need to check that after as well. But anyway, for instance, do we have the instruction JSR? Yeah, we do. Do we have jump? We do. Jump indirect even. Or what about the direct jumps? Or is there such a thing? I don't know for now. Okay, guys. Okay, doesn't really matter that much. So I'm no longer taking your time. I believe that within the next videos we're going to be implementing the set operations. And by the way, once we're done with the set operations, instead of going for the next instructions, I would probably, and yeah, probably I would even, well, I can actually go step by step. Yeah, I'll probably go implementing this step by step and create it. So these just require custom tests and custom implementation, so I can reuse the code. But these are the one opcode operations, and that should be not that difficult to implement. Okay, doesn't matter. So once we are done with the set operations, we then can try to implement the logic of taking the user input from the keyboard and outputting the values, outputting the characters. And I'm being inspired by the Apple I computer from 1976, and the memory addresses being responsible for input and output will be taken from there. I've been mentioning this in the intro video for this series, right? So yeah, that's gonna be the case. So it would be quite pretty fun probably to see how this code not only gets executed, but I mean, like, how this code actually starting doing something. Well, actually, we're not going to be able to use the real code from, let's say, Apple I, because we don't have the jump instruction yet, and echo there involves the jump. So yeah, it's not really that clear for me at the moment how this is supposed to be done, but we'll see. Okay, guys, yeah, this is it from my side. So thanks for watching. Until the next time, and take care.